Okay, this is a excuse me, this is a continuation of we're on lesson 7. Last couple of slides of the Extrema notes. Here we have a reminder of the first derivative test, which is used to find local extrema at a critical point. Here are the rules. If f prime changes sign from positive to negative at some critical point C, f has a maximum there, local max. If f prime changes negative to positive, it has a local min. If f prime does not actually change sign at C, there is no extreme value. So that's typically what we're using to pin down local extrema. Finding absolute extrema is a little bit more elaborate. It's possible that local could also be absolute, but we also have to check endpoints. I think we talked through this in the previous video. We need to check endpoints when we have a closed interval because endpoints can be the highest or lowest point. To find absolute extrema, we make a list of candidates, which includes critical points and endpoints. And then if possible, try to evaluate your function at all the candidates to find out which y value is the highest, which one is the lowest. We've got another example, f of x as stated from -3 to 3, both included. So I imagine we'll be checking endpoints at some point. Some prep work. I'm going to go ahead and find f prime. I'm guessing we'll be setting that equal to 0. That'll help us find critical numbers. In fact, once you find the derivative, it's helpful to factor that in order to find the various zeros. Here I'm setting this thing equal to 0. I see solutions at 0, plus or minus 1, and also positive 2. So that's actually the answer for part A, critical numbers. I'm already setting up my number line for f prime. I've got my endpoints, all those critical numbers, and then again, pick numbers within each subinterval to test if f prime is positive or negative. And then we use all that info in part B. It says find the x coordinates of local max and min. And we're just looking at our sign chart here. Now, the sign chart, AP graders do not count this as justification. It's nice to draw it out to help yourself, but the act of drawing this does not mean you have actually justified anything yet. You have to write a statement probably in words. So I'm going to say local min at x equals -1 and also at 2, because that's where f prime was changing from negative to positive. Likewise, local max at x equals 1, since f prime changed from positive to negative. This is the important thing to write out to get credit for your justification. Let's find intervals where f of x is increasing and decreasing. Again, justify. We do that by, again, looking at derivatives. Here I've said f is increasing from -1 through to 1, and also from 2 to 3. That's where f prime was positive. F of x decreasing from -3 to -1, also from 1 to 2, that's where f prime was negative. I have a little note here. Remember, increasing as a vocabulary word describes intervals. So in my sign chart, I temporarily stop at 0. Technically, f prime is 0 there, but that doesn't mean that we're not going to include 0 as increasing, because it remains true that points to the left of 0 are lower, points to the right of the 0 are higher. That's a weird little trick, but it would be technically incorrect to try and disregard 0 here. That is amongst the interval values where we keep going up and up. So basically I'm saying even though f prime hits 0, no slope, that's only for a brief moment. You do actually still continue to increase on that interval. Find coordinates of absolute max and min. Well, we already had candidates from part A. We're going to add to that the endpoints. So -3, -1, +1, 2, 0, and 3. Plug those all back into the original function And that's the most straightforward way to see what's the highest y value, what's the lowest. Turns out our max was at -3, but give the full ordered pair. Minimum was at x equals 2, give the full ordered pair. We'll do some more work with this stuff in class, and we'll also look at some calculator examples in class eventually. One last slide reminds us of a very important theorem from Calc A, a mean value theorem for derivatives. It says, if a function is continuous at every point of a closed interval and differentiable for the corresponding open interval, meaning just the interior points, then there has to be at least one location, perhaps x equals c, within that interior interval at which f prime equals f of b minus f of a over b minus a. It basically says instantaneous rate of change derivative equals the average rate of change. It could happen more than once within an interval, but it has to happen at least once if you have satisfied these requirements. Okay, here's a quick diagram of what's going on. I've got a continuous differentiable function on an interval. I draw a red secant line to represent the average rate of change in the interval, and I've identified a point in the interior whose instantaneous rate of change happens to be the same as the red. They have the same slope. Okay. Which of the following functions fails to satisfy the mean value theorem? We have a collection of functions on given intervals. Okay. The first one, well, here we have a fail. And that's because when we differentiate this thing, we see that the derivative would not exist if you plug in x equals 0. That means there's an interior point in our interval that's not differentiable. So there's no guarantee that mean value theorem works in this instance. Okay. The other three all work out. Okay. Now you might say for part B, well, that's an absolute value graph. It's going to have a corner, so it's not differentiable. You're right, but that corner is going to occur at the vertex, which is x equals 2/3, and that's not the interval that I'm asking about. So if we only go from 1 to 2, yes, this thing is differentiable and continuous, so mean value theorem could apply. Polynomial, this one's pretty straightforward. It's differentiable and continuous everywhere, so definitely from 0 to 2, mean value theorem would apply. The fourth choice, this thing is not defined if x is less than 2, but that's okay because that's not the region that we're looking at. From 3 to 6, yes, this is differentiable and continuous. All right, final example. One last f of x, one last interval. Can we find each value of c that satisfies the mean value theorem? Okay, so we're basically saying, let's find the actual locations where the instantaneous rate of change from 1 to 4, or for somewhere between 1 and 4, matches the average rate of change. First step would probably be to determine what is the average rate of change from 1 to 4. Slope formula from algebra. F of 4 minus f of 1 over 4 minus 1 is a 1. So now we know we're trying to find places where the instantaneous rate of change, the derivative of this thing, is equal to 1. And that's why I figured out the derivative over here using shortcuts. I immediately set it equal to 1. I do get 2 solutions algebraically, but we're going to disregard the solution that doesn't live in the interval of interest. So the only answer that we would report is 2. So the mysterious c value that satisfies this thing in this case would be 2. Write the equation of the secant line connecting the endpoints. Okay, so writing the equation of a line in this class, usually you're going to go for point slope form. We already know the slope of the secant line. If I want to pick a point, let's see here. You know what? I might actually have a typo in this equation here. Because Oh no, this works out. This is not a typo. If I plug in x equals 4, that would be a point on the secant line. Okay, sorry, I paused the video there, make sure I didn't screw something up. But yeah, no, this is good. When I plug in x equals 4, that's one of the endpoints that we're using to construct the secant line. I plug in a 4 here, or rather right here, I get back a 4. So 4 comma 4 is a point that lives on the secant line. So pair that with the slope of 1, we get y minus 4 equals 1 times x minus 4. Last part, write the equation of the tangent line that satisfies MVT. The tangent line, okay, we're talking about, this C value up here that we already found. We know the slope there matches the average rate of change. So the slope is still 1, but I need to find the xy. X is 2. If I plug a 2 back in up here, I get back a 3. So 2 comma 3 is the actual point where the tangent line is parallel, same slope as the secant line. Here's my final point slope form, y minus 3 equals 1 times x minus 2. All right, that concludes the lesson 7 videos. Let me know if you have any questions. Thank you.